Everybody, I'm going to show you today what SDC Verifier is and how it works and connects with Simcenter and why it is important that you can make that connection directly within Simcenter. SDC Verifier, I'll briefly explain, that is a program which is an add-on, and the idea is that we check, the first idea is that we check your models according to standards, and the second thing is that we make very extensive calculation reports, and both of them can be very useful for Simcenter 3D users. Okay, so what are we going to discuss today? I'll show you what is SDC Verifier, what is the general idea, the program structure, and we will show you some examples of usage, and then Jarko will take over and show in a small demo how quickly and easily this software is to use and how it integrates within Simcenter. And then in the end we will have time for questions. What are general types of structures where SDC Verifier is used? You can see a lot of maritime and offshore structures. Wait, I need to change my pen. Yeah, okay. Now, yeah, I can make a picture. So here you can see an offshore structure which was completely modeled and calculated within SDC Verifier. We have lattice structures, big complicated structures where you need to do a lot of checks and a lot of load cases, like aeroplanes, moving parts which can all be implemented together like this equipment crane, and large one where fatigue is a big item like cranes. These are just examples. Of course you can add this to all kinds of other structures you have too, but this is just a first idea. So as you can see, SDC Verifier is an add-on which works directly within Simcenter 3D, and if you have here a button, you can open up the separate window of SDC Verifier. The reason why it's not completely all buttons integrated within Simcenter is because we have too many options and there's not enough space. So the reason, that's why we want to keep separate window. But it is important to notice that you work on the same model. So the big advantage of using SDC Verifier over other code checking programs is that you check your design according to standards in the same model as you do your other FEA calculations. So you don't have this clutter of transferring model results from one program to the other. It stays within Simcenter 3D. Then we go to the scheme. What does SDC Verifier do? We start with a general FEA model that comes from Simcenter, and then we add the following steps. We have a load combination part, we have a recognition part, checking parts, and a automatic documentation part. And we will go through that one by one. So load combinations are to check according to a lot of different situations, which in general works, which you need in standards. We need to recognize structural parts in your model because checks are not on elements but on structural items. So we recognize these things. We have, of course, all these checks. We have a lot of implemented checks, as you see here in the middle, and you can build up your own if you want that too. And then extensive reporting is stored afterwards. And the nice idea is if you have your full calculation set up, you can update your model, and then you can click on request a new report, and everything, the full circle is filled in automatically. So it saves a huge amount of engineering time. So that is a very big benefit for the Simcenter 3D user. Okay, So the first step is load combinations. The idea is if you want to calculate according to standards, you need to use the same calculation structure. So that's what we offer. We start with general base case loads, or individual loads as we call them. For example, mass loads, a hoisting load, wind loads, storm loads, test loads. And you need to combine these with different factors, and these things are in general specified by standards. So you have different load situations where you have a factor within where you take 1.23 times 1 of gravity, for example, and 1.64 for from hoisting or another load. So you separate the base cases from the load combination. How does that look in SDC Verifier menu structure? So here you have the different base cases, like gravity load. In this case it's a tip load, a load in the middle on the bridge, and then we have two wind loads. So these are calculated separately, and then the resulting load combinations is all done internally within SDC Verifier. And since it's based on linear combination by default, it is a very, very fast method to make a lot of load combinations out of a few base cases. If you, for example, so if we take a load set number 4, then we have a combination of the gravity plus the bridge load with a dynamic factor and a wind load combined, and you can make these combinations within Excel. So you can see here that the gravity, that load case 4, which is this one, that is this load case. You can also add a safety factor, which is used for checking according to yield or buckling. Since you use that for different types of groups, we added this safety factor as well. And then if you have this, in this example we only have 8, otherwise you cannot see it in the screen, but if you have much more load sets than these 8 here in the example, you would like to group results all together. For example, if you want to have working conditions and working conditions with wind, then you can see here in load group 2, that is the working conditions with wind, so that is load case 3, 4, 5 and 6. And if you want to plot, for example, the maximum stress in working conditions with wind, you can plot the load group results, and you get then the maximum stress of each of these underlying load sets. So that is a quick way to check, to see in a single plot if all underlying load sets are, if they comply with standards. Not only we can handle a lot of load cases, it comes together with some nice extra tools as well. If you have a lot of load cases, in this case we had an example where we had 132 load cases, and we wanted to figure out, okay, that's nice, but if we have overshoots or if we want to update and change our design, we would like to know, okay, which load cases give the maximum stress at which position. So we have in this plot over here, we can get a plot for any criteria: maximum stress, maximum buckling factor, maximum fatigue result, all these kind of things. We can set, okay, what is the governing load of according to this criteria on what element, and then you can see that only 8 load cases are determining in this case. And in this picture here you see at which spot, which load case it gives you the maximum stress. So that makes it very nice to see, okay, if I want to optimize and modify my model, I need to know which load is governing at which location. So this is a nice extra tool to figure out, okay, what are my load cases where I need to pay more attention to. So this is about the first load combination tools. We now go to the second part, which is recognition. The recognition of structural items. In order to make these checks according to rules, these rules are on beam members or joint, for example. If you have lattice structures and if you have plated structure, they are on stiffeners, plate fields on plates, on panels or on, for example, on welds, and you can check welds according to fatigue or strength, for example. What is also nice to see is that since we recognize this, we see all the important parameters which are used to make a check possible. For example, if you have a beam member, you need the most important input is the buckling length. So if I take, for example, from this joint to that joint, that is the buckling length of this member, but only in one direction, that is in the horizontal direction. While if I'm looking at the vertical direction, the buckling length is twice as long. And how do we do that? We recognize the connection, so this is what we call a 3D connection, while this is only a 2D connection. So a 3D connection has a connection in all three directions, while 2D connection has only stiffness in one plane. And that means that this 2D joint here does not split over the principal in the vertical plane, so over the principal axis. It does not split the buckling length. And why is this so important to have this automatically determined? If you miss this double buckling length, so if you have standard code check programs, they use a single element to define this, to go from joint to joint, and the buckling length is then by default the element length. And then the user has to take care for himself that the buckling length, in this case in the vertical plane, is the double length. If you forget to do that, your results are 4 times off, because the buckling risk goes with the square of the length. And so it's extremely important that you recognize all these things together. So this is one thing we recognize. The same is for plates. We recognize for each plate, we recognize the length and width, and also if it's inclined, for example, we update the stress direction according to the plate orientation. The same with welds. Yeah, so it is important to, and what you also see in this example is that the recognition is mesh independent. It doesn't matter whether you have a lot of elements, like what is shown here with these welds, or if you have the coarse elements model, like what you see here with these ships and this relatively large elements per panel. You can even have a single element per panel. And how do you recognize these different items? We see that based on the structure of your FEA model. And this is all automatic. Jarko will show that in the demo, that it is really fast to recognize. And if you want to modify something, you can do that too. Then we come to the third part, which is the checking part of our software. We have a lot of implemented codes. We have civil engineering codes like the Eurocode and the AISC. We have offshore code like ISO, NORSOC, DMV, API, ABS, and we have some lifting codes implemented as well, like the DIN and the FEM. And if there is, the nice thing is you can see here on the right that the structure of the standard and all the formulas are completely open. So you can copy a standard, you can modify it, and you can password protect it under another name. So it gives you a lot of extra flexibility as well if you want to modify an ABS rule, because for example Lloyd says, yeah, well, the ABS rules are fine, but this formula here, we do not fully agree with that. This Poisson ratio combination factor should not be 0.3 but 0.5. They say, okay, fine, we do that. You modify it, password protect it, and even before you show results, you can show to you can prove that you calculate according to this modified result. So this extra flexibility is appreciated a lot by our clients. And then the last part, which is also extremely important, is the reporting part. Everything you do, if you have a lot of load cases, we had here in this example, we have 9 load cases which we want to see. You want to be able to store all these results, even if you want to show, if in the engineering phase you look only at the maximum results. So for in the engineering phase, in general, you look at the load group results. But if you want to show if you want to get approval, you need for every load set, you need to have your results documented. So what is the idea? You set up this what you want to show for one single load case. When you're done, you copy that to all other load sets. And again, the nice thing is that everything you do here will be saved, and if you update your model, you get exactly the same report, but then with updated results. Yeah, so this is with this tool, the design and updating program goes much quicker. If we look at the full calculation report, we have different options. We can, for example, the first and easiest way, first and easiest report is the model setup report. That is a full description of your model with, for example, for each material type, for each property, for each property, each component, what constraints are there, which loads are there. And for example, if we take here this material, you can see, okay, how many elements are defined with this material? What is the total mass? What is the center of gravity? What are the properties of this material? And also what are the tensile and yield stress in a material case? And not only that, so this gives you a very good overview if you to check if your model is fine. You can give it to a colleague, or you can give it to a regulator, or you can give it to the designer to see, okay, look, this is what is in our model. You can see if everything is according to what you if you made a design change, you can see if that's still correct, and you can update it, you can compare, and you can see that in a PDF report. You don't have to sit one next to the other. This is a very nice way of storing and reporting the full description of your model, and it's completely automatic. Jarko will show this too, I hope. Then we go to the next part. I already explained a bit. So in this case, we have load set 2. We want to see first the description of what is this load set, what does it contain. So it has the gravity plus the seismic acceleration in X direction plus the seismic acceleration in Z direction. The total sum of forces is shown, maximum and minimum displacements, a displacement plot. Probably in the page later you can add a stress plot. You can zoom in to stresses, and if you're completely satisfied, you copy exactly the same results to all these others as well. Yeah, the same works if you want to do a check according to standards. There you can set up the same description per loads and per group, exactly the same way. So if we zoom in more in detail, the structure of your calculation completely comes back into your job description, so your report description. Okay, and yeah, so we have described now the load combinations, the recognition, the check part, and the reporting part. And since you can store this full thing, I just repeat this. The biggest time advantage is that if you update your model, all this tedious work is now after setup a single button click. You should just click, okay, can I get an updated report, and all these things are done automatically within. Okay, so if you work with SDC Verifier, that also has a positive change into your workflow. Because at the beginning of the calculation, you can quickly set up with where you do a full calculation procedure. So you check on yield, you check on plate buckling, you check on weld strength. You do all the checks at once instead of what you normally do. Okay, let's first do a check on yield, and when that's okay, then we go to plate buckling, and then we go to welding. Because normally you do that because you cannot get all the overviews you get, you cannot store that. So by storing this in this report, you can see all the possible problems all directly at the beginning, and then you get directly all results, even if they're not correct, and you have a complete reporting tool directly ready at the beginning. And then during the design process, since you have this report, for every design change, you can see for all the important things you need to check, you can compare that with the previous result. And you can see, okay, is my design change really an improvement, or where do I need to change? So in the design phase, this goes much quicker. And at the end of the project, there is another very nice thing which we figured out later, that if you use SDC Verifier, even last minute changes, which you normally say, well, yes, sorry client, well, we cannot update because making a report takes 2 days. We cannot do these last minute changes. I need to update all my pictures, all these kind of things. With SDC Verifier, that is not a problem. It is only calculation time of the computer which limits you in the time. So a last minute change, let's say for a day before the deadline, can still be updated. Of course, the conclusion and summary you have to write yourself, but everything else is automatically updated. So that makes the complete design and engineering phase much quicker. So we made an estimation how much time can you save with SDC Verifier if you combine that with Simcenter 3D. We have, if you look at the first phase, the modeling and calculation setup, you can save maybe 20% because we have an easy way to make all these load combinations and to keep track of what is what and how to set up these things and what are the different checks. So there is some time gain in there. Then of course in the reporting phase, since we can make very extensive reports by just copying all the settings to others, we think typically you save around 80% in reporting time, and the biggest part is you save during the design update. Since you have everything already, you have all the problems already indicated from start on, the design and updating phase goes much quicker. You need less updates, and you can quicker compare. You can see the influence of your updates much faster. Yeah. So overall, if you save 50% typically on the design updates, 20% at the initial phase and 80% in the reporting phase, the overall FEA engineering time is reduced by more than 40%. I think that is quite a good argument to use SDC Verifier, even if you do not do any code checks at all. Okay, so this is the short overview of the total program. I will now quickly go through some examples with pictures, and then I want to give the floor to Jarko for showing showing how it works in real life with a demo. Okay, so if we have, for example, fatigue checks, we recognize all these welds. What do we need to set in the fatigue? You make groups of load combinations with a number of load cycles, and you can, so that is on one side you only have to set the usage in fatigue groups, and on the other side you can make a difference between welds and non-welds, as you can see in the picture. So the first thing you do is, okay, for the full model we say no welds. We in the table we use the classification according to lifting rules to show you that different methods of classifications are possible. Then you can override for all welds in the weld direction, so that is the stress in that direction. We can use a good quality FAT class, so that is the vulnerability to fatigue. If that one is a K1 is a pretty good quality, and that is, if you transfer that to FAT class, it is 140 megapascal, while at 2 million load cycles. While a stress perpendicular to the weld only has a fatigue resistance of 19 megapascals at 2 million load cycles, so that is considerably lower. So you override that in the SDC settings with all welds perpendicular to the weld. We set that as a K3. Then we need, for the shear, we also need to set a K0. That's a standard classification. And then there's one extra thing is if you have intersecting welds, you always have a stress perpendicular to the weld, so that one also needs to have a low factor. And then you can see, for example, that is why this one and that one give higher results than its neighbor elements, either towards the middle or at the edge. And then you can, so this gives you these 5 steps after recognition gives you a very realistic result, where you see popping up peak stresses, peak fatigue damage factors at the welds, and where there's no welds, you can see everything is pretty is okay. And that is a big change compared to other programs who give result like a big red spot over here, and with the story, well, if there is a weld, then you might get a problem, but if there's no weld, then it's probably fine. This is much more accurate. And not only, so to give you an example, this is a crane we did. This is a 40-year-old crane, so then we can even track if the calculation and the usage factor over these 40 years. We calculated that, and after that we could do inspection, because you cannot inspect a 10 kilometers or 100 kilometers of welds. You first need to see where to look for. So we found overshoots in the weld calculation, and we looked there and we found a crack of 20 centimeters wide. So the client was quite happy that we found these things. And this is a very good example to show that the recognition within Simcenter is typically something which helps customers doing quick fatigue analysis, and realistic ones as well. Another usage for recognition of welds is the weld strength. In standards, it's allowed to summarize the total load over a weld and divide that by the total load capacity, depending on weld parameters like the A height, or if you have a partial penetration weld, you can even set the H, S, and R. You can set these per weld separately, or you can set all of them for. You have simple tools like, for example, all the welds should have at least an A height of 4. Then you select a couple of others. You can set half the plate thickness. So there is a quick method to set for the different welds different parameters, and then you get a result like this. So you have, for a single weld, you sum up the total load over all the welds, and you divide that by the total weld capacity. So here you see the total sum of forces and moments over the weld, and then you can calculate the weld capacity based on the standard rules according to DNV, for example. And why is this important? If you do not use this method, you will see in your FEA model at the end of your weld always peak stresses, because the peak stresses at the end are there, but for the weld strength capacity, that's not a problem. If you have some initial shear or a plasticity due to shear at the tip, that is taken into account in the formulas, because they're based on ultimate limit strength. So if you do this, you get a single result per element, and that is a real result, the same as what you would have if you would do a calculation. You can see a full weld, or is either good or not, and you can see that all these red ones need a bigger A height, while all the others are fine. Another example what we use, where you use SDC Verifier for, is plate buckling results. If you want to do if you want to calculate a ship or an airplane or anything where you or any plated structure, you need to prove that every plate segment has the buckling of each plate segment is the buckling limit is above a certain specified value, and they take and you need to use the stresses on the plate in the plate direction and compare them according to standard rules, where they specify, okay, if I have a plate, I have compression in that level, compare that with the allowable, and then in that direction as well, and again also for shear. So we do this completely internally. And if you have, for example, it doesn't matter if you have element stresses For example, if you have here, then you have element directions which might be completely chaotic. We update these stresses internally in the right direction of the plate. Yeah, so you can either show over the full plate, yes, it buckles, or here it does not buckle. Yeah, so that it gives you the answer you want instead of an approximate solution where you check the stress for each element on the plate. You have, for example, I've seen customers building something similar like this, and then they calculate the critical stress in the length and width, and they compare the single element stress with that. But the problem is, if you have a plate which is half over and half under the limit, then you still don't know whether it buckles or not. So we summarize this thing according to the standard, and then you can get, okay, is okay according to the standard or not. So this is a very quick method to make these intensive hand calculations quickly and accurate according to the standard you need to apply with. Beam member checks, the same issue, of course. I already explained about the plate buckling, the lengths. If you follow the checks, you can see, again, everything is open. You can see that we follow the standard and the standard chapters. So if you have a bending stress check, we do that, shear stress check, an actual and bending, and we have one overall check as well. So you can check them, and you can see here the maximum utilization factors and one overall. So you can see that, for example, in this situation, the 0.9 overall utilization factor is based on actual plus bending, and the bending part is 66% or 66%, and the actual loading is around 70, and combined it ends up in 0.92. Yeah, so it gives you also a clear idea, okay, what do I need to change and how much do I need to change. The same for joint checks. In joints we recognize the shape, so the angles, the distance between the pipes and all these kind of things, and also the load pattern. It makes a difference if you have a force which goes in here and goes out there, or if force goes in and it goes out there. In the 70s they set up all kinds of formulas to figure out these jointed connections, so these lattice structures with formulas, and the advantage of these formulas is that it's an extremely quick method. The drawback is that you need a computer program to figure out how this works, because this is no way you can do this with hand calculation only. You can do that for a single load set and a single joint, but if you have 10,000 load cases, and even in this very short model we only have, let's say, we already have like 50 joints, so that's an impossibility. You need to have a code checking, and with SDC Verifier you can do this directly within Simcenter. This is how the checks work. This is I think due to time consideration I'm going to skip that, but the general idea is, okay, it is very easy to read. You know, you can see that the allowable stress is set up with a factor, and the utilization factor is this stress divided by the allowable stress. If you have in general you need to do that for every stress direction, so you have 6 stress direction plus an equivalent stress direction, because you have very often a specific rule on the equivalent or Vomises stress as well. Since we have the 7 results and we will only want to see one, we add number 8, which is an overall, and that gives me the absolute result of the 3 principal direction, the 3 shear direction, and the equivalent one. So if I plot this utilization factor in the overall direction, I am sure I will, if that one is below 1, I'm sure all these 7 checks are below 1 as well. Yeah, so that's a very quick method, and it is an open structure. So if you want to make something slightly more difficult, like a bolt check or a rivet check, you can add these with formulas, and you can add the pre-stress in a bolt as a parameter instead of calculating that in nonlinear calculations if you want. And you can make this as simple or difficult as you want. You give, for example, another parameter which is not in your model. You add that like a friction coefficient. So this is the general idea of SDC Verifier. We quickly go to the overview. So what does it do? You can do, it enables code checking in Simcenter 3D. You have a lot of code checks and general FEA results. You have them combined together in a single model. So you do not need to build up a second model and transfer results and geometries and all these kind of things. Everything done within the Simcenter 3D model. So that is a very strong way, like the Siemens idea. Okay, you want to have a single database and not some stuff here, some stuff there, and updating all these different models is a nightmare. Now with SDC Verifier and Simcenter and Inix, the basis of your of everything is the CAD model. We have a lot of standards available. You can customize them if you want. The reporting is very, very extensive, and that can be handy for approval, for storage, and another nice thing is with all these things you have the total calculation procedure saved, and that enables you to save a lot of time in the design process. So that is in a nutshell what SDC Verifier does, but that is all, of course, nice talking. I think we should swap to Jarko, who's going to show that what I promise here in this presentation is actually true. So Jarko, I want to give the word to you.
Okay,
and
thanks.
The screen as well.
Yeah, but maybe there are questions on your presentation, so we give a minute while I'm switching.
Yeah, that's okay. That's a good idea. Are there any questions? Oleg, can you see if there were any
Nobody typed the questions in the conversation, but yeah, you're free to ask some now.
Okay.
So do you see my screen?
Yes, I see.
Yeah,
it.
I do.
Okay, then I'm going to start.
Yes,
so we are going to run today an example of plate backwing check on DNV and ABS on this model, part of the ship. So we have Simcenter 12 and I'm start SDC Verifier. First I'm going to show you how to create a new project and explain basic idea of SDC. Then I'm going to show load combinations, envelopes. Then we will do recognition of plates, plate backwing check according to DNV, and reporting. I will do quickly. If you have some questions after each stage, you can write that or ask, and we will stop to answer. So to create new project in SDC, you just make a new project. We have a button here that gets active model in Simcenter opens. So it gets my model pass to SDC. Here I can define the data, the project number, and the name. Demo. Also, I can add some details about who is creating this report and for whom is created, but I will skip that in this demo, but because it can be also added later in the report. So a new project is created, all the data is read to SDC. I would like to show you the this is the model part in the tree. So I have here materials, properties, fem loads, and constraint are red. So it is corresponded here to Simcenter 3, also has a constraint and loads. So I have it here. Then when the model is read, first what we do, we create a setup our calculation scheme. What we have to do first is create individual load. Individual load, it is combined boundary condition, fem load plus constraint. So here I have the list and I quickly can create all my loads I would like to analyze. So I select all fem loads and constraint and press create. So in my model I have 5 boundary conditions created. Then when I did that, I have single individual loads. I have to do load combinations. So I go to load sets And I create that one by one. As Walter explained, I can add gravity, for example, and ballast load and give them a factor if I want. So give a name, let's add 1, press create. I can do that one by one, or we have also the tool which creates them a lot. So we go to menu. I will show you that one because it's more efficient way. Create multiple. So I have prepared in Excel to be quick and efficient in this demonstration a scheme which I would like to create 12 load combination with different factors for basic 5 individual loads. So I just copy them from Excel, go back to SDC, press from clipboard, and I get my load sets immediately in SDC. When I press OK, they appeared in my structure, and I can see I combine gravity with ballast crane inside with different factors and so on. So same is easy to modify the structure, and it can be included in report as well of the description. After I did that, I would like to create an envelope. Envelope, that's to know the maximum displacement, maximum stress among all my load combinations. So I select them, add to my envelope, give it a name. Envelope is used to get a maximum results over all your load cases, and also for fatigue calculation, because we can get the stress difference among all the load combinations. So when my structure is set up, so calculation core is done, it's time to go for a standard. We need to start from recognition first. So we go to menu recognition, panel finder. Fine. So I see the wizard for recognition of backwind plates. So as you can see here, we have a section in X, Y, and Z direction, which corresponds to frames, longitudinal index, and custom section, which are inclined section or curved sections. What I need to do, I need to only press find all. And if you can see, all my recognition is done. So I have 5 frames, 9 longitudinals, and 6 decks, and 3 custom sections. So I'm going to show you with some plots how it looks like. So I will make a demonstration of all frames with colors.
Jarko, maybe a short intro. I see that the screen is sometimes a bit lagging, so maybe that's just me, but don't be too quick.
Okay. So I can go back and a bit explain with section, because section is here is written the coordinate and how many backwind plates is recognized. So I will do some, and this is a backwind plate. I will make a picture, I think, for this to show you. So we have a special plot which highlights with different colors the backwind plates and with the number. That you can see the corresponding number if you want to know. This plate has AD 83, and here we have the numbers of that ADs. You can easily find where they are. So the dimensions of the plates are recognized automatically, length and width, but if your stiffeners was not modeled or due to other reasons, you can modify them manually and change. For example, if I want, I can change them and set to the desired number. To check if everything was recognized correctly, we have the tools to plot the dimensions with labels on top of backwind plates. So you can do that for all sections or for single selected section. I will pick one frame to show for an example. So if you can see, on top of in the center of the backwind plate, there is dimensions length and width, always shown. That's in this picture. You can check if all the dimensions are correct. So after you did the check, we also we have an export possibility that you can export plates of by different criteria to groups and components. I will skip this due to lack of the time. We will go to filter because this one is important. If your model has fine mesh, then recognition goes smoothly. But if, for example, you have coincident nodes in the model, or other problems can be that some plates can have not recognized dimension. That's why we have in the filter and options undefined dimensions. We say apply. In this model, we can see we have a course good model with no errors, so we don't have undefined dimensions. So we have to do the checks to be sure that everything was recognized correctly. I will show you briefly one more example. For example, if we want to see all the triangle plates in our model, we can do that. Say apply. As I can see, I have 5 plates which are triangles. I can see them in my model. So this is 5 plates. Okay. When everything is recognized and checked that you are happy with the parameters, we can close Panel Finder and we can go to the standards. In the standard section, you can see we have 11 implemented standards. So ABS, we have 2 revisions, and plate buckling DNV also 2. So I'm going to show you an example for DNV 2010. So when you click on that, you see the wizard where you should define some parameters required by the standards, like resultant material factor, and also how do you want to treat the stresses on the buckling plate. So here you have that options, and also it has some notification options, like you need to use yield stress of materials in your calculation, and wizard reminds you that you have 7 materials in your model where you don't have the yield and tensile stress defined. So I will do that for all of them in the wizard form. So I will set as these parameters and press OK. Now I don't have materials with not defined yield. Also, here I can define what sections I want to check. If I want to do only one specific, I can set that. And then if I press OK, my standard is defined and added into the structure. As Walter mentioned, everything is open and you can see all the formulas. So I will demonstrate that one. All the formulas, we have here 27 formulas in total, are written, and you can even, if you want, you can select the formula and modify. So this is the editor where you can write your own formulas with we are not going to change that, but also what I want to show you, that our formulas has a name and also the description. In description is usually the reference to the formula from the standard. So when the standard is predefined, we are ready to do some calculation. I have project which is stored and everything is calculated, to not to spend time on this during the demo. So I will open the plate buckling final project. And now I'm going to show you a few examples of the results we do for envelope. For example, SDC, as Walter mentioned, with one picture you can see the worst results among all load cases. So I pick stress, equivalent stress for my envelope, and SDC will display me the highest stresses among all load cases on one picture. Also, SDC has some advanced tables where you can see, for example, if you want to check, you can check in one table. For example, I can check all my load sets. I would like to see the worst stresses among them also in the table mode. So we have a table for each direction. We have stresses for each load set, and also it is highlighted for each direction. It is minimum and maximum stress with aqua and red colors. Now also I want to show the tool which Walter is mentioned in his presentation about governing loads. For example, for this model, I would like to see what loads give me the highest stresses on which elements. So I select equivalent stress. I want to see governing loads for full model, 100% of elements on my envelope. If I do that, I see now the distribution, how much elements has the highest stresses, which number of element had the peak stress and the value. And also I can make a picture of that. So you see with the color. So each load set have a color, and with labels you can see that. So for example, green color is corresponding to load set 9. Those element has the highest stresses from which is governing loads 9 is for them. So we can do that for stresses, and same is available for plate buckling check. We can also see the which buckling factor is caused by what loads. I will demonstrate that a bit later. So that was results for the envelope and the governing loads for stresses, and now we go to the plate buckling results. So we have specific dedicated tables to demonstrate results for plate buckling. So I would like to see envelope. So immediately the worst results among all load cases. I'm not interested right now to go one by one for load cases. I would like to see all sections and show the governing loads. So if I press field table, so this table is summary for each. I have here frames, longitudinal decks, and custom sections. And for them I have a table with the dimensions of the length, width of the plate, thickness, stresses, and buckling factors. And also here is the governing load. So on this section we see the worst plate with the highest buckling factor. So it's basically summary. If we want to go into details, we also have some options here to say show plate results and show only the plates which fails. I will do that in the moment. So for example, in frame 1 I have 2 plates which fails, has results above 1. So here we configure this with this option.
And please do not forget that this recognition of all these sections, sections, decks and longitudinals, is recognized automatically. So that is takes around, for this model, how much time does it take?
Recognition
15 seconds?
It was less. For this was 3 seconds, I think.
Okay.
So here you have a possibility to see only the sections which fails and the plates in this summary table. Also, we can also display a plot. We can define which sections we want to see. Actually, I selected gravity load by mistake, so I would like to see envelope. Much more interested. So this, as you can see, we use for buckling result the legend, which is from 0 to 1.2. So which is above 1 is orange and red result. So you can identify which buckling plates are failing. But we want to use this option. I think that would be. We want to see that I used option for plate buckling to show the maximum buckling value per plate. So if I have a failing value, it will highlight my plate with that value. So it's easy to identify which plate fails, which not on your model. So after we did that, we can go to, I will show you also the governing load example I created. So I want to see the same like for stresses. I have 4 load cases which are causing the result higher than 1. Let's see. So here I have, I defined my criteria to show only elements which are above 1. So I see elements which are failing and which load sets are governing. So when you did all the calculations here, it's time to go for reporting. So I have already predefined report. So usually what we can include in report, the description of your models, results for your load cases, job results, and also results for your checks. So I will show you on some examples how the description of the model looks. I will go to Simcenter, go to this mode, and I would like to generate, for example, one material. So here I can see that elements which belongs to that element are highlighted, and I have how many elements, what are the mass of that element, center of gravity, and all the characteristics. Same I can do for the properties, thickness of the property, elements, and how many elements, which is type, which material is used. Also we can document the FEM loads and constraints. Also I'm going to show you the results. So as Walter mentioned, we have set up, like you can see, for each load set same results. We have same setup, displacement plot and table, and also stress. So I'm going to our report is real time. You can generate part of the report. It's not necessary to generate the full report and see if you are not happy with how your picture looks or the number format. You can generate only the part. For example, one table, if I want, I can generate. I can see result. If I'm happy with format and layout, so I can later generate full report. So I will show you the standard layout for the one load set. So here I have this description of the load sets, then it's sum of forces, displacement table, the displacement plot, and on the next page I have same for stress. The minimum on the full model I have, this is extreme table, which shows the minimum, maximum, and absolute stresses on my model in X, Y, shear direction, and equivalent, and also equivalent stress on the picture. So as you can see, we have in SDC, you can configure the legend. So we do displacement plot and stress plot, and we have different legend. You have an option where you can say what the scale should be for different categories. I will show you that in the moment. So for example, for stress, I say the limits that I want to have my legend set from 0 to 240, and for displacement, automatic scaling in 10 levels, and for stress 12 levels. So for Buckwin factor, we use different legends. So that's, you don't have to change your legenda. You have to configure what category should be once. You can store that to library and use on other projects. So that also saves time. And same we have for formatting numbers. You can say how you want to look your numbers in the table. Stress, for example, in scientific format, displacement in general format with two digits after dot. So it's possible to make a configuration for full your report. So this is about the results. Also we have for example, that's the content. The load sets we created here is shown. The loads and the factors are combined, so that is documented. Also, the summary tables for load sets. In one table, you can see that I have stresses over all my load sets, and also displacement. The worst displacement over all my load set, and also I have the summed forces. This is check we do on our models. What are the summed forces for all my load cases, and also reaction forces, sum of applied and reaction forces in my model. So after that, after that we can go to Buckwin results. We set up the scheme. We did that for envelope, the worst results, and since I know that my governing loads, there are only 4 loads, so load sets 5, 7, 9, and 11. I'm not going to include in my report all 12 loads, but I did the envelope and only governing loads. So, and I will show you how the typical the general frame look like, and also one typical frame. Because so I have overview. I make a table with 5 frames in one table, and the worst results, and also the picture. And now I have it in detail for one frame configured, so I can see each frame. I can see the orange and red plates are failing, and in the table I can see what are the result dimensions of that, the worst plate, stresses, and the buckling factor. So this is set up for everything. It's very easy to combine. If you set up for one load, you just make a copy paste for other loads. So I have same structure for loads at 5 and 7. So in this report, I'm not going to generate in this demo because it takes few minutes. We are going to generate it after that, and we will send it with email to all the attendees. So I think that's it for my presentation. So if you have any questions, please ask.
Okay, Jarko. Thanks. I think that was a good demo. We will make another one based on beam buckling somewhat later, and then maybe we can organize a new one. And we will put this on YouTube as well, so you can also show this to your customers.
Maybe one thing I can mention, that structure is flexible, so you can easily move your items. You can put up, down, and also you can control. Here you have a properties. You can say, do you want to have this this table from new page, or I will show you that on example. For example, I want this plot to start from new page. I just change that and it goes to new page. So you have a full control over the structure in this designer mode.
Okay. Any questions? Maybe? Diego, maybe?
No, it's clear, the demonstration.
Okay, good. Well, then I want to thank you all for this meeting, and we will send you a link we make a YouTube movie out of it. We send a link to that, and then you can use this same presentation for your customers.
Okay, yeah, that's perfect. Thanks a lot.
Okay, good.
Okay.
Thank you.
Okay, thanks and bye. Thanks for your attention.
Thank you. Bye.
Thank you. Thank you, Walter. Thank you, Jarko.
Okay, thanks.
Bye.
Bye.
Okay, bye.